ready as you're going to be? Okay. Any questions before I start in? Things you've been wondering about? Yeah.
On the pre-lecture, one of the questions was about the speed of the electrons, and it said that the correct answer was that it was actually the electrons themselves.
That was that for this lecture?
Yeah.
Yeah, okay. I thought I had, yeah, I'm covering that today. It's in the book. What's your concern?
I guess it was just confusing because in the book, I never really read it, or maybe I just couldn't find it. It didn't say anywhere that it
So, how fast charges move in the circuit? So you can have a reference after this as well. Page 411 in chapter 23 called Speed and Source of Electrons in a Circuit. That whole section is it. And so although an electric signal travels at nearly the speed of light in a wire, the electrons that move in response to the signal actually travel slower than a snail's pace. So yeah, there's a whole section on it. I just encourage you to reread it again.
Yeah, no, I guess I couldn't find it.
So in the 11th edition anyway, it's 411, or chapter 23 on electric current called Speed and Source of Electrons in a Circuit. And that's great since we're on it. 411?
Yeah, 411.
That's on 412, the last sentence in the first paragraph on page 412. And let's discuss why that is, because that's a point I wanted to bring up today. A lot of people think that when you flip a switch, and the lights come on, like that, they picture electrons whizzing around at the speed of light going through the circuit. I talked about a little last time how it's we're not paying the power company for charges. We already have them. So all the charges are in place. So the wiring from the light switches over here, that's just like, okay, we close the switch, and now it's like the charges have a path to get over to there. Well, they're already there in the wiring up to the light. That's probably a bad example in this room because they intentionally put these lights on a 3-second delay. Watch this. Push the button. 1, 2, 3. But that was just so it wasn't, That's electric programmed in. The current is already there. So, point is, once you close the switch, what happens is you now establish an electric field at nearly the speed of light. The electric field's established because there's a difference in voltage. The energy on one per charge, remember, voltage is energy per charge, is different at one side of the circuit versus another. After it goes through stuff, it uses up energy. As it goes back to the power supply does work on it to separate the charges and gives them energy. So now there's energy per charge. And then they go through the circuit and use up that energy, the signal. That's basically what electricity is. So once that path is closed and you can see both sides, there's an electric field established. And that's like the commander in military saying, all right, forward, march. And then all the electrons, or charges, start to move where they're at. So the charges or the electrons themselves aren't going that fast. But the signal, the electric field, is what's zippy. So the electrons already inside actually those are LEDs, inside the LEDs, they start moving as soon as you flip the switch. Don't think of it as dominoes. I used to. Like a bunch of ping pong balls lined up, and you hit this one, and it bumps into the next one, and that makes this one bump and bump and bump, and that's how the signal travels. That's not true in charges. They all just start moving at the call of the electric field. Forward, march. Yes?
So the signal of the electric field is what happens.
Yeah, the electric field can travel nearly the speed of light.
The electrons are already there, so they go.
They're accelerated. They feel a force by that electric field. Electric field is force per charge. Let me write that for reference. Electric field was the force per charge, just like acceleration was force per mass. So, just place something in our gravitational field, boom, it immediately feels the force. But the force of gravity, that's, never mind. Where I was headed with that, it was going to come out gibberish anyway. So now the charges do move, mind you. This one, say I'm a charge, I'm an electron. I'm in a conductor, so I'm free to move. I can dissociate from my atom, no pun intended, and go over. I might be grabbed by... Thank you. That was great. I needed that. So I started feeling that influence, and I start accelerating. But immediately, what happens? I run into something else, or another atom grabs me as an electron. But then I'm accelerated free again. But then I might bump into something. The momentum of the the kinetic energy. I might actually be moving this way sometimes, but slowing down, or run into something. But I'm always being accelerated that way. So over time, the electron might be going like this. So over time it drifts. And because overall there's an electric field trying to move the electron, say, that way. Now here's a review question. If I'm an electron and I'd start drifting with time that way, point in which direction the electric field is aimed. Very good, that way. If I were a proton, which way is the electric field? Yeah, positive charges go in the direction of the electric field. So in my example, yeah, the electric field would actually be established in this direction. Good. And so, yeah, over time it's kind of slow. While I'm on that, that's for a DC circuit. There's two types of circuits, DC and AC. Who's heard of the band? But yeah, that's what they named it after, AC/DC. DC stands for direct current, and AC for alternating. I'll write that, because those are important. So direct current is when the current flows in one direction. The electric field is established and it doesn't change. It's always in one direction. That's batteries. They work that way. This power supply, for example, it has two switches. I can provide direct current, or I can provide alternating current. So as the name implies, that one alternates. Your outlets, like this, provide 120 volts of AC signal. That means the electric field points one way, but then it switches and points the other way. And then this way, and then this way. And it does that 60 times a second. That's what 60 hertz means. It's 60 hertz, we're going to learn in the next unit after the exam, is a unit for frequency. It's the rate at which it changes. Cycles per second, 60 times a second. And so in that case, an electron gets accelerated one way and does this drunken drift dance. But boom, in a 60th of a second, it starts drifting the other way. And every 60th of a second. So over time in an AC circuit, the electron hardly goes anywhere. It's hardly moving at all. But in DC, it does, over time kind of drift, but very slowly. Yeah?
So if you're to plug into an alternating current, how do the electrons get from one place to the other? If they are getting pulled back and forth,
Basically, the electric, yeah, they themselves physically don't really, over time, they're still in the same spot. They've moved, they've gained energy, and they've wiggled because we applied a voltage, electric potential. Write that again because they're the same thing. And that was our energy, electric potential energy per charge. This is just to represent that it's electric potential energy as opposed to gravitational potential energy. So yes, all those charges that are already in place, when you establish this electric field due to this voltage, you're giving each of them a certain amount of energy. It makes them start accelerating, but back and forth if it's AC. And that's enough energy in the filament of this light bulb to make it glow. You know, if it's everything else is right. But what's say that again? G? Think about it. I just didn't hear the first thing you said. So, bottom line, charges themselves don't move that fast, especially the electrons that are freer to move. They do drift. They are in motion, but they don't really get displaced. This one's slowly, this really not at all. But each of those charges has gained energy when the electric field's established. Let's do a little demonstration here. This is an LED light bulb at the end of this wire. I turn it on. What color do you see? Yeah, it looks orangish to me too. This actually has a red and a green LED, two of them in there. And I don't remember, but for argument's sake, let's say when the voltage is positive, the electric field's in one direction, the red LED lights, not the green. When it switches directions, the green lights, not the red. So these are alternating 60 times a second for lighting. The red one will light 60 times every second, and the green one will light 60 times every second. But yeah, they're flickering. But it goes so fast we don't notice it. And it'll be cooler with the lights all the way out. So I don't know if camera, you want to just focus over there while I got the lights on. Tell me when you're ready. You good? Because I know it's hard to focus in the dark. So here it is. So if I displace it, while it's blinking, you can see that it's turning on and off. So you can see the red section. That's where the AC current and voltage, for that matter, are going in one direction. The electric field's in one direction, so the charges are being accelerated one way. And then it switches, and it's the green. Do you see the black spot in between them? That's where the power company's gypping you. You're not getting any voltage at all. It's not being accelerated one way or the other. Are you concerned? No, you shouldn't be. It's just where it switches direction. It's just like if you throw a ball up in the air, it stops and comes back down. But remember at the top, it's still accelerating. It's just being pulled back. It's changing direction. So again, here's the light, kind of mix of the red and green colors, but it really is alternating like that. Let's turn the lights back on. So it looks like this. AC, it increases positively and then increases negatively and then positively and then negatively. This is AC because it's alternating. The voltage does that because the electric field's changing. And so the current established, the flow of charge, changes direction. So the current's doing the same thing. It goes one way, slows down, and then goes back. And then slows down, and then goes back. And so it looks like this too. So well, FYI, we say this is 120 volts coming out of the outlet. But it's not fixed. It's not 120 like this. It's always changing. It's 120 here and there, and maybe negative 120 down here. here and here. But over time, it actually gets up to about 170 and negative 170. And here, what is it? Yeah, that's 0. That's the black spot. That's when it's going, and it's actually, for a brief moment, it's like there is no electric field because it's changing directions from one way to the other. But it is changing, or going that, just reversing direction. So some of you have probably heard, this is called, and I'm not holding you to it, but the RMS voltage, root mean squared. Because it's always changing, what value do you use? This value. We could use the average, but what is the voltage on average? 0. That won't help us. So we use this thing called root mean squared, RMS, which is 120. And lo and behold, by coincidence, no. If we were to do all your electrical calculations at 120 volts, you'd get the same values when you do things if this was DC at 120. It's one reason they chose RMS, to how it works out. So you could light up this light bulb with 120 volts AC or 120 volts DC. This one will work. Even though in one, it's only going in direct, always in the same direction, DC, or AC, always alternating. The filament doesn't care as long as it's getting 120 volts, 120 joules per coulomb of charge. Yeah?
So for every outlet that operates at 120, is this electric potential going to be the same?
Yes, every outlet. That one, this one, this one, this one. Yeah, in the United States, they're rated at 120 volts AC. Now you know it's actually fluctuating the whole time, but the quote-unquote average value, not the actual average value, this RMS value is 120. Some devices don't work on DC and some don't work on AC. A light bulb will work on either.
Why do we choose AC?
Great question. Why do we choose AC instead of DC? We could have. I encourage you to read more about it. It's called the War of Currents. Historically, you can Wikipedia it. Bottom line, they figured out AC, how to make it work practically and cheaper first. Now we have enough to where you could actually generate 120 volts DC and make it work. You would have to implement things differently, but yeah, it could work. But now we've established AC and we're used to it. Many things need AC, not DC. We convert back and forth all the time with some electronics. But the main reason, we're transformers. Transformers we haven't covered yet. But when current goes through a coil of wire, actually through any wire, when charges move because of an electric field, if that electric field changes, AC, not DC, if it changes, it's that change that actually can cause charges over here in the vicinity of this conductor. They don't even have to be electrically connected. Like you could have a coil here, and AC goes through there. So it's going one way, then the other, this way, then the other. You could have another coil over here just nearby, and this one feels the change in that electric field. And that makes charges over here start moving. That's a transformer. You have your primary coil and your secondary coil. And so you can get current out over here. You can step the voltage up or down. You can step the current up or down by the turn ratio. How many turns you have. You can't, though, create something out of nothing. What do you think that is? We've done that before. You can't create energy out of nothing. So when you step the voltage up using a transformer, the current has to go down. They go in opposite. We did that as power. So remind you, power, which is energy for time. the rate at which we use energy. Remember, current is the flow of charge. So it's charge moving at a certain rate. That's current. The flow of charge. And voltage, we've already reminded you today, is the electric potential energy per charge. So energy per time, power. So a transformer, even though you can use it to step up voltage and whatnot, if you step the voltage up, because energy has to stay the same, is conserved, the current goes down, or vice versa. And that's useful to transmit electric power, this energy per charge, to our houses. It was easier to do with less losses, less expensive to do that if we could step the voltage up and send it at high voltage, which is why our wires have high voltage and they're up there on insulated poles where we can't touch. So historically, they learned how to do that, and that only worked with AC because we needed that change in electric field. Transformers, this stepping up and down, doesn't work with DC because it doesn't change. You can think of the energy transferring to the house at nearly the speed of light. Because as soon as I plug something, as soon as I turn this switch, boom. You know, the power company, it connects a switch to there, and it's like the electric field's established. And boom, we now have a potential difference, which means the voltage is different on the two sides of the circuit. We have a lot of energy at the beginning, and you can think of it as coming back as nothing. So each charge everywhere in there gains energy per charge. So think of voltage that way too. Voltage is like the push. If you have a difference in potential, electric potential, difference in voltage, then you're giving energy per charge. The electric field's established, and they want to start accelerating. Water is a good analogy with current. We talked about current, water in a stream, and it's flowing. How would you get water to go uphill? What's that? I heard a few things, but I couldn't. It was too quiet. You can increase the pressure down here, the difference in pressure to pump it up, right? Or lower it here to pump it. So a pump, I like to think of as a battery or a power supply, the power company as a pump, in a sense. It's providing the energy to all the charges I already have. It's pumping them. It's trying to get them to move. They're giving the charges the energy that I need to go flow through my circuit and deliver that energy to whatever, my light bulb, my capacitor, whatever, my LEDs. So this is like a pump, and it's pushing the water or the charges around. But the energy is conserved. We just started out with electrical energy, and we turn it into heat or light or whatever. Good questions. Well, what's that? So you've heard there's less energy wasted in AC because it produces less heat? And do you know why you heard that? Why AC would produce less heat?
Because it's changing.
So the idea is that it's alternating, so one way gets up, but the going the other way kind of effectively cancels it, so the net effect is less? Okay. We'll have to look into that more. I've never heard that. And my off-the-cuff explanation is that doesn't seem to make sense to me physically. In both of these, the charges themselves are vibrating, and they're moving around. In DC, they might be like this, moving. But over time, they kind of drift this way. That's what we call the current. And the current's not going that fast. But the electric field, this energy per charge, it gets them moving. And so when they run into things, that can create heat. AC is doing the same thing. But over time, it kind of stays put. So they're still moving with the same amount of energy per charge. And so that could still cause the same thermal agitation and heat. So in my mind, that alone, they would both get equally hot. For example, I know for a fact that 120 volts through this makes it light up. It's a certain brightness. That'll be a certain heat, hotness, get to a certain temperature. If I turn it off, let it cool, do it all again with 120 volts DC, which is this half, it'll be identical. Same brightness, same temperature, and same color. So the direction shouldn't affect heat. What it goes through can affect heat. Resistance, absolutely. Absolutely. Let's discuss that. That is, where's my chalk? I was going to do that today anyway. So see, this is great. So we now know what affects this flow. That's the current. It's proportional. I think I've been switching in this class. Let's see, this or this. Which ones do you guys like? I've seen both. The top? Yeah. Fine. As long as you guys know, I mean, it's proportional to. One, the push. It's proportional to that difference in voltage. Because the charges won't move if you have the same potential. And the obvious one, if it's 0 here and 0 here, nothing's going to happen. If this is 100 and 0, or 120 and 0, now we know something's going to happen. There's a difference in potential. But if this is at 120 and this is at 120, nothing happens. Because there's no difference. They're the same. So you make that difference bigger, and that'll push more charges, give more energy per charge. The current goes up. You'll have more current, more flow of charge. Likewise, though, as you brought up, the current is also proportional to resistance, R, resistance. And that's what it's going through. Think of water again. You got a big, wide pipe. You can get a lot of water through there. The current is big because there's not much resistance. It's easy to get through. It can go this way, or it can go this way. It can go over here. It can go over here. There's lots of space. Now, constrict that tube. And it's really narrow, like a straw. It's harder to push the water through, isn't it? Because it's restricted. From Bernoulli's principle, we know that the speed of the water will, very good, increase. Which will do what to its internal pressure? Decrease in the narrow part. Good. See, we reviewed. Okay, back to current charge. So narrowing it, like in that example, there's more resistance here than here for the current, the flow of charge. And if it's harder to get through here, in a circuit, an electrical circuit, you don't get as much current. The flow rate here actually does change. I wish that one stayed consistent, but it doesn't. You can't shove as much current through. So we put these two ideas together, and it's Ohm's Law in your book. And it's that the current is proportional to these two. So let's back up to this one. If we increase the resistance here, what happened to the current? It decreased. So we've learned that's inversely proportional. they go opposite. If you increase the resistance, this goes down. If you decrease the resistance, it's easier to get through. This goes up. So that is the change in voltage over the resistance. Some people write this or remember it in this form. They're the same thing. That's Ohm's Law. It's our guide to thinking for the relationship of how much charge is flowing in our circuit, the current. Increase the potential difference, more energy per charge, you can move more. But increase the resistance, make it harder to get through, you get less. Let's do that with this circuit. Plugged in, okay, turn it on. 120 volts DC is going through this resistor, a bunch of wire, and then the bulb and back. I can change how much wire it goes through. And I bet you can tell me what happens. Okay, ready? What do you think happened to the current flowing, the charge flowing, the current in this circuit? Yeah, it increased. It got brighter. It delivered more energy. Each charge had more energy. More energy per charge was delivered to the light bulb. So the current went up. So I must have done what to the resistance? Decreased it. Yeah, it's going through less turns. Let's make it go through more turns. So much it's hardly even lit. Now it has to go through more wire. Think of it as longer. Not just the size, but if you had a wire that's, say, that long, it won't have very much resistance. But what if you had a wire that went really long, right? That's going to have a lot of resistance because it's more to get through. So yeah, increase the resistance and less current can flow. For the same push, this has the same voltage. It's still 120. It's still trying to pump the same amount through. More resistance lets less through. Less resistance lets more through. That's Ohm's Law. Absolutely how a dimmer works. Basically, when you turn a dial, you're essentially changing the resistance and thus how much current flows in the circuit. And that's nice and hot because this has resistance. And as it goes through there, it's a really, really skinny filament. And so a light bulb has a lot of resistance compared to going through this wire that hardly has any. And so when it meets resistance, it heats up. Absolutely. And whether it's AC or DC, going this way or this way. Let's do this one. This is a cord. There's 3 prongs on most cords. We usually talk about 2. Do you guys know why there's 3? And one's a ground. What are the other 2? You can think of it as positive and negative, hot and neutral. The hot usually has where the energy's at. Lots of volts. Let's say 120 volts. 120 joules per coulomb. Generally, neutral is connected to ground. But it doesn't have to be. It could be floating up somewhere. But neutral is generally lower. And ground is 0 volts. It's at 0 potential. So there's actually 3 things. It's not like, again, you don't think of it as charge coming from the power company in the hot side, whoosh, through the circuit, whipping back out the neutral or ground back to the power company. No, they're already there. That just establishes the difference in potential. So I'm going to take some pencil lead, a skinny conductor, so it'll have a lot of resistance, but it essentially is like shorting it out. In this one, which is typical, the black is hot, so this will be 120 volts. The green is ground, 0 volts. White is neutral. We'll see if it's grounded. So I'm going to do the obvious. I'm going to put it between black, hot, 120 volts, and ground, 0. Balance it across there. Completes the circuit. Plug this in. Turn it on. Are you ready? Poof. That's why you don't stick your fork in the socket. I don't even, oh, here it is. So, the electric field was established when I hit the switch. The charges in here started moving, but it's really skinny. Lots of resistance. And as the resistance increased, we got less current that could flow. But it's really skinny. It heats up. You saw the sparks. It blew off. Anyway, it got the whole brunt. I mean, this isn't much resistance compared to a light bulb. It essentially like shorted it out. But that's because there was a difference in potential. Let's do ground green. We know that's at 0. And neutral. Put it across those. Plug it in. Make sure I did. Yep, it tripped the breaker. We'll reset it. Ready? Nothing. Why? Make sure it's working. You got it. Nothing. I was resetting and resetting. Why nothing? Ground's at 0 volts. Neutral must be at 0. It is. In most circuits it is. It should be. In everything we normally deal with. You can also do then hot and neutral, and that would do nothing as well. Since it's not exciting, I'm not going to do it. So in theory, because I know physics, I could touch these two, nothing would go through me. You'd be all fine. Electricians know this. They can work on a live circuit as long as they don't touch the live 120 volts. I'm at 0. I'm attached to ground. So I can touch 0, ground. No difference, so no charges flow. If you know neutral's ground, you can touch that one. No problem. I can touch them together. Nothing would happen. But if you touch the hot, zowie. Ah! Oh, no, just kidding. It's not. Because that's 120. The other side's 0, and that would give all the charges in me some energy, and they'd start moving, and I wouldn't like it. Let's unplug this too for safety. Let's send it through this wire. Here's our light bulb. A real skinny wire, lots of resistance, but it's just a conductor. Plug it in. Actually, this looks cooler in the dark. We'll dim the lights a little. So I'm going to send a lot of volts through it, across it. It's going to push a lot of energy through it. Ready? You can see it heat up. It glows and burns. That's what your light bulb would do if it wasn't enclosed. It would just oxidize with the air around it and burn out. That was the hardest part for Edison. What happens is as it goes through it, it burns it up. And it gets skinnier and skinnier and skinnier, which increases the resistance more and more and more. It heats up more and more and more and burns up. So that's how a fuses could work. If you put this in your circuit, let's say this is in series. It has to go through this and then through your appliance. Let's say something goes bad with your appliance. The resistance drops a lot. I don't know. Something breaks. If the resistance drops, what happens to the current? Yeah, it increases. There's a spike in current in your circuit. But it also goes through this, the fuse. And if more current goes through this big resistor, it could blow it, just like we saw. But now, there's a break that stops the power, the energy per charge over here, to hopefully protect your appliance from getting fried further from whatever happened. Or say the power company or lightning strikes. There's just a surge in power. More current tries to flow. It'll burn this up first before it blows this up. So a lot of people with the fuses, oh, it says it's a 10 amp fuse. 10 amps, a fuse. Remember, amps is the units for current? Well, that means it'll blow if it gets above 10 amps to protect your circuit. Some people say, oh, it blew, so I need to put a new one in. Oh, I'm going to put a 20 amp in. That'll be better. because 20 is bigger than 10. It sounds beefier, right? Well, that means it won't blow until it gets to 20 amps. Too late. So actually, you want a lower number fuse to protect your things more. But if you go too low, you're not getting enough power and it won't run. So it's usually to go with what's recommended. That's how fuses work. Let's store some energy, shall we? Batteries. What they do in power supplies, as I told you, they provide the energy for charge. So chemically, here's some samples. Chemically or electrically, they separate charges, and it takes work to do that. But now they're ready. These have the electric potential energy that they can deliver to the charges. Capacitors work that way. A capacitor is just an insulator sandwich. Styrofoam's an insulator separated by two conductors. So like this. That forms a capacitor, and you can store charge on it. This is a capacitor, a really beefy one. Inside, there's a whole lot of this, really small. So it can hold a lot of charge. But we need to separate the charges. How are we going to do that? I'm going to plug it into this power supply. I'm going to turn it to 4,000 volts. If you care, it's DC. It's going to run in one direction. I'm going to turn it on. Okay, now this is delivering power to this. And that energy, we're separating the charges. It's like we're pulling the positive charges onto this side and the negatives onto this. It takes energy to separate opposite charges. Opposites attract. You have to overcome the Coulomb force and pull them apart. They build up. There's more positives on this side, more on this side. What though, let's turn it off, disconnect it from the power supply. Now it's all on its own. I'm going to short it through here. I'm going to give it a path. There's charges stored, separated, and it has energy. I'm going to release that energy through this conductor from one end to the other. It's like going like this. And let that potential difference flow through here. Ready? 1, 2, woo! I like that. Let me ask you a question. What charge is this capacitor? What's the overall charge? Very good. It's 0. It's still neutral overall. It still has the same number of positives and negatives. But we've separated them. You can think of it as being polarized. We did energy to do that. So this one by itself might be positive, and this one might be negative, but a capacitor together is not. So I'm going to end, I think, with these last two capacitors. We'll have a good weekend. Didn't get the circuits. I'll have to do just series and parallel circuits Monday, first thing, before the review. So here, the batteries connect to the capacitors. These are little guys. They're charging up, using energy to separate. And I must not be connected as well as I'd hoped. All right, charging up, separating them, doing work. They're increasing their voltage. Now let's connect the capacitors to the light bulb. They go through the filament and use up that energy. In the last 5 minutes, this is a capacitor. It's a bottle of water. It's called a Leyden jar. This is the outside conductor, and the water inside is the inside conductor. It's sandwiching the insulating plastic. So it looks just like this. I'm just using a pop bottle to do it. I got a screw in the top to touch the water inside. So if I charge this up, separate charges, and I'm touching the outside, and I touch the inside, it's just like doing that. We can get current to start flowing, charges to move in my circuit, me. This one's a lot safer. That was scary. I'm not touching that. This is totally safe. I need a human electrical circuit. Who would like to experience what a little charge moving through you did? Some of you shocked yourself last time on the Van de Graaff. It's not any worse than that. It's safe. I wouldn't do this if you're going to kill you. Unless you think you have a heart condition, don't bother. But come on down. Let's form a circle up here. We could do the whole class. It'd be great. Actually, the more of you that volunteer, it's like a longer circuit. What happens to the resistance as we add more and more people? It increases. And if you increase the resistance, what happens to the current? Decreases. It won't hurt as much. So the more of you, the better, actually. Come on down here, form a circle. Hold pinkies with your neighbor. Oh, that's it? Come on. Where else do you get to experience electricity like this? So I'm going to charge it up. I'm going to use the Van de Graaff over here. I'm going to turn it on. 2, 3, 4. That's probably enough for our circuit. All right, now in theory, I've used that energy to separate some charges. Who wants to be the switch? You get to touch the top. All right, I'll get in here. And we'll hold your pinky. Now, things to observe. We all have to be connected or it doesn't work. In other words, if you break, let go, it can't see both sides of the capacitor. There's no electric field. The charge is in you, and you won't get energy. They won't start moving. Now we complete the switch. I'm touching the outside, one side of the capacitor. You touch the inside when you're ready.
Do you want me to keep my finger on it?
Oh, you'll know.
Okay. Maybe we should have. All right. Oh, that was good.
Thank you guys for helping. See, that wasn't too bad, was it? Now, I've calculated this. I know how much energy this can store, energy per charge, and I know what typical resistances are. I've calculated this. You can get the current. It's not that hard. Look, if I know the energy per charge, which I do, I can measure, and I know our resistances, I know exactly how much is flowing through us, and it's very, very, very small. 2 things, observations, and I'll let you go. 1, you were afraid to touch the switch, weren't you? Yeah. However, when you close the switch, boom, the electric field is established like that. We're all full of charges, and all the charges started moving about the same, everywhere in the circuit at the same time. So you didn't feel any more touching the switch than the rest of us did. And did you notice we all about the same time? That's because we have the charges. We felt the same amount at the same time. The electric field is established like that. That was a series circuit. The current in a series circuit is the same everywhere. As it went through each one of us, we used up some of the energy. And then it came back, and it's all gone now. With a capacitor, I'd have to recharge it. With a battery, it's until the chemicals are used up. Yeah, Glenn?
Can't you do that with, what is it, when you have like the glass bulbs and there's the electric,
Oh, those. Yeah, when you touch it, you're essentially grounding it. There's now a difference in potential, and charges are flowing through the gas to you, to ground. And when they go through the gas, it glows. Yeah. So the only parallel circuits, I apologize. So worst case, I can delay those questions, but I think you can figure them out. There's just a couple on the homework, or email me. We'll finish up series in parallel Monday. Review for the test next Wednesday. I know it's coming. Yeah, I'm